Welcome to our second to last piece of the landing performance series we're doing with the CJP safety video podcasts. We're going to talk today about snow considerations during landing, and we're going to also talk about crosswind considerations, our last two major topics. And then we'll have one more summary and some takeaways. Okay, so we're going to discuss snow a bit. So far we've been talking about water, mostly wet runways and contaminated with standing water. But we are going to continue now into snow-covered runways. So the Canadians have attempted to quantify the condition through the CRFI, Canadian Runway Friction Index. Of course, if we're flying to Canada, this is particularly useful information for us to have. But even if we're not, there's some interesting takeaways we can get from this. So the CRFI is an instrument derived test. It's mounted on a vehicle, measures deceleration force. It's on a scale from 0 to 1. 1 is representative of a dry surface. Important to note that because of limits inherent in the testing, there are a fairly long list of conditions for which a CRFI will not be provided. So it's not provided for just a wet runway. It's not provided if there is slush on the runway. It's not provided for wet snow. It's not provided for over an inch of dry snow. So this really is primarily of value for dry snow conditions, although there are some other conditions where you might see this. So here's an example of a CRFI report for Frobisher, Iqaluit, Canada. This is showing a CRFI value of 0.34. It also shows the runway that was taken for, the temperature, and when it was taken. So 0.34 would be the value here, again, on a 0 to 1 scale. What's interesting is the Canadians publish a table that shows the expected range of CRFI values by what conditions exist. So again, on the left of the horizontal axis here, we have effectively no braking, and on the right, we have dry runway performance. And so the further the line extends to the right, the better the braking, the further it extends to the left, the worse the braking. What I find particularly interesting about this chart is when we look at the bar that is the longest, that has the largest range of expected CRFI values, it's for one of the conditions that we would probably encounter the most frequently, which is a thin layer of dry snow, 3 millimeters or less. So again, that's the typical crossover point where we start considering a runway to be contaminated. So for less than 1/8 of an inch of dry snow, we could potentially experience everything from 0.16 to 0.76 CRFI values. And we're going to look at what the implication of that is on our expected stopping ability. So the way we would use that CRFI value is in the Canadian AIM. There's this chart that is published. We start on the left with our unfactored dry runway landing distance. Then we enter the chart, find the column that correlates to the CRFI value that we have had reported. And then to the far right, we would see what we expect. I'm sorry, under that column, we would see what we expect for a recommended landing distance. So for example, in the case of a citation that expects to need 2,800 feet of unfactored landing distance, and with a CRFI value we saw at Frobisher of about, let's say, 0.35, we would start at 2,800 feet, go over to 0.35, and we see the value is 5810. That value represents a 95% level of confidence. In other words, 19 out of 20 landings on a CRFI of 0.35, an aircraft that needed 2,800 feet to stop, if it was dry, should be able to stop in or less than 5810. But again, 1 time out of 20, that would not be enough, emphasizing the importance of some safety factoring. The second piece we want to talk about quickly is crosswind considerations. There are a sizable number of runway excursions and light jets on a contaminated runway. where the aircraft does not depart the end of the runway, but rather departs the runway laterally. And a crosswind is often involved in this. To review our SOPs, we recommend that as the braking action reports decrease, and these again also correlate to a runway condition code that we can look up and use as well. For each step down, we recommend deducting 5 knots from the maximum demonstrated crosswind component. Our SOPs recommend that the maximum demonstrated crosswind component be treated as a limitation, even though we know it's not typically a restricting limitation for aircraft. So we would start with the maximum demonstrated and then take 5 knots away for each step down from good braking. Why is that? Well, when we think about our airplanes, we have a large vertical surface aft of the center of gravity called our vertical stabilizer. The entire point of our vertical stabilizer is to make our aircraft directionally stable. What that means is the aircraft wants to point into the relative wind. When we are on the ground, the relative wind is simply the surface wind when we're not in flight. When we are on the ground on a dry surface, of course, the friction between the tire and the surface prevents the aircraft from turning into the wind. But if you imagine taking this citation and placing it on a perfectly frictionless surface, then the aircraft would always turn and point into the wind, even resting on the ground, because of this large vertical surface after the center of gravity. The aircraft wants to point into the wind, and it is only the friction between the tire and the ramp or taxiway or runway that prevents it from doing so. Well, when we land on a very slippery surface with a crosswind, what happens is, as we are now on the surface and are no longer in flight, the aircraft wants to weather vane. It wants to point into the wind. It is, again, only the friction of the tire and between the tire and the surface and any rudder effectiveness and or directional braking that we have that can be applied. The friction between the tire and the surface will, of course, affect how much directional braking we can apply. So as the friction decreases, we're losing on 2 counts, and our rudder effectiveness will decrease as our airspeed decreases. So we do see a sizable number of runway excursions where the pilot is not able to counteract the weather vaning tendency as the aircraft starts slowing through the ground roll, ends up with a lateral runway departure. Again, the accident history is replete with examples of this particular case. The aircraft had a 80-degree crosswind of 14, gusting 25, with light rain reported at the time of accident, and that water on the runway and crosswind combination of the two resulted in the aircraft departing the runway laterally.